Hello everyone. First, I'm sorry that I can't join you in Canada due to the visa issues, but I'm really grateful for this chance to share our team's research about making road safety better by measuring water on pavements. Okay, let's start. We all know when water stays on roads, it causes hydroplaning. It's a big reason for accidents, and it also slows down the traffic and makes travel less efficient. So a real-time, cost-effective in-situ measurement of pavement water film thickness is critical for early warning. There are different types of sensors for this, but microwave sensors are the best for roads. They don't cost much, can measure a wide range of thickness, and work available outside. But here's a problem. Real ones have impurities, like de-icing salts or dust. This makes the water salty. Salty water changes how microwave pass through it. It soaks up more microwaves, stops them from going deep, and makes the sensor's measurements wrong. So we need a way to fix this salinity problem. So in this work, we made a system with two key parts. One to measure the water film thickness, and another one to measure salinity. So let's explain how it works. First, the whole system is put inside the pavements. Its outer layer is made of PPO, a strong material that keeps water out and protects the inside parts. When the microwave hits the edge of different materials, some bounce back and some keep going. The antenna checks how this reflected and transmit waves change as the water changes. From these changes, we can calculate how thickness of the water film is. So the main part is a small rectangle antenna, which sends outside the 2.4 GHz microwaves. So why we choose 2.4 GHz? Because this frequency is allowed for small, low-power devices. It's part of ISM band, no license needed. Its microwave comes from a small antenna inside. It goes through the PPO layer, then water film, and finally into the air. So we simulated how salty water affects the antenna. For example, the electric and magnetic fields around the antenna. The effect of the water film on the amplitude and phase of reflection are simulated. Both of them change with the water film thickness, but when the water is saltier, this change gets weak. That's why we need the second sensor. So the second sensor is a sanity sensor, like this. To measure salinity, a four-electrode configuration is used to ensure accuracy of the conductivity measurement. It has four small platinum rods inside the strong PPK materials. We send a small electric current through the two outside electrodes, then measure the voltage between the two inner electrodes. This voltage tells us how conductive the water is, and the conductive is corrected with the salinity. So, this conductive data, we can fix the thickness sensor's error caused by salt. So, and next, we tested the system to see if it works. Here's what we do. We put the sensor in the cell-made pavements with the tall refractometer to check the salinity for sure. The system is fast and it takes only 0.6 seconds to measure and process data. It's good for real-time warning. The sensor works perfectly. The environmental results are in agreement with simulations. After salinity-compensation, the measurement system can be much more accurate. The measurement range is up to 7 millimeters and conductivity from 0 to the 8 Siemens per meters. On average, our accuracy improved by 77.9%, enough for the most road situation. So, make a conclusion. We made a system that measures water film thickness on pavements and fix errors from salt. It's a cheap, fast, and works well in real-world conditions. All the PCBs, a microstrip antenna, and a four-electrode structure are fabricated and encapsulated in the PPO substrate and aluminum shell. Its work greatly improves the detective accuracy of the water film thickness in the complex road environments. So thank you for your listening. If you have questions, I'd be happy to answer them remotely. Thank you.